unit 1 and really 2 is like understanding graphs. Stay down, thing, or else you're gonna block everybody. Cool. Okay. Understanding graphs, like what's going on? Understanding functions. I don't want to even say graphs, but you guys can think graphs when I say understanding functions. Unit 1, Unit 2 is like, what are functions going up and down? How are they going up and down? Where are some of the zeros? Like, just like, what is the shape of this equation, of this graph? Cool? Today, and Unit 1, focusing mostly just like on how functions are changing. How is this function changing? And we will talk about how functions are changing rates of change. Okay? Cool. And I had my helper in here, and I told him, here's a complex function, please graph it. Okay? And my teacher aide haphazardly graphed 3 points of the function. He graphed this 1 point at 2, this 1 point at 5, and this 1 point at 1. Okay, 2, 5, and 1. And cool, this is a good start. I'm asking you, how much did the function change from this 2 to 5, and how much did the function change from 5 to 1? Tell your neighbors, how much did the function change from 2 to 5? Beautiful, beautiful. All right, many of you said the following. We went up 3, and we went down 4. I'm okay with that, but I'm going to show you in a second how I'd actually like you to consider the y's, like going up by saying I would like increase 3, positive 3, that value. It's like I went up 3, I'm going to put a value versus a word. And down 4, I'm going to say like the y is like decrease by 4, or like negative 4, I'm going to put negative 4. Okay? All right. So good start. Next question is, where was there more change? 2 to 5 or 5 to 1? Tell your neighbors, what do you think? Was there more change? Okay, great. Like everybody's like, oh, 5 to 1 because we went down 4. Seems like more, right? Okay, good start. 4 is more than 3. So you answer 5 to 1. Great. What we just found is called a net change. Okay, a net change. Now, how can I do something with the numbers 2 and 5 to get plus 3? And what can I do to the numbers 5 and 1 to get negative 4? Where I'm doing the same thing. Like, how can I get this number positive 3 and minus 4 using a mathematical operation with my numbers? Tell your neighbors. Tell your neighbors. Tell your neighbors. How can you find this change? Yes, I'm going to say, and this is important, that if you take a finishing value and you subtract a starting value, you will get an overall change in your value. Okay? So I'm looking at the change in my y's. I took my y that I finished with, and I subtract the y that I started with, and this is how I got 1 minus 4, or sorry, 1 minus 5 is negative 4. I finished at 1, but I'm starting at 5. I got negative 4. This is how I go 5 minus 2 is positive 3. I finished at 5. I started at 2. I got positive 3. Subtracting values gives you change. Okay? Cool. What is the major problem with the graph that's given to us? Tell your neighbors. There's no context. There's no x value. There's no context. There's no x value. Okay, so the student, my teacher aide, went back and said, okay, turns out with my function, when you plug in 0, you get 2. When you plug in 2, you get 5. When you plug in 5, you get 1. Okay. Now we have some more context. Now we can talk about the change between 2 and 5 and 5 and 1, but make it more comparable. Because if you notice, and many people didn't, the space between these 2 points, like going from 2 to 5, it seems like we went up 3, but over a smaller like length here than we went from 5 down to 1. It took longer for me to go from 5 down to 1. You see how like you didn't notice that the spacing between the 2 points was different. Since the spacing is different, actually the values +3 and -4 are not values I want to compare because they're not spaced the same way. So having these x values are important because we can see the spacing. So try to use these values 0, 2, and 5. So you kind of figure out the spacing and use that along with this +3 and this -4 to create comparable things. What would you do? Like, now we can say, oh, I went up 3. Okay, never mind. I went up 3 while I went over 2. That's cool. Like, that's good. Oh, that provides like, oh, I went up 3 over the course of this interval, the space of 2. I somehow need to take these numbers 3 and 2 and kind of combine that so I can compare it to here. I went down 4, but over a space of 3. How can I kind of compare these things better? Tell your neighbors, what can you do? If it's coming to you right away, great. If it's not, it's totally cool. I heard an S word. Linda, what'd you say? Slope. Slope. Oh, I heard rise over run. I heard some people just say like, yo, let's like divide those 2 numbers. Let's take this +3 and divide by 2. Let's take this change in my y's, the net change in my y's, I went up 3. Take the net change in my x's, I went right 2. Let's divide those 2. And I get now a number 1.5. It's a number. We'll talk about what that number means. Here, let's take the change in my y's. I finished at 1. Again, finish. I finished at 1. I started at 5. My net change was down 4, -4. Over the course of finishing at 5, starting at 2, a net change of 3 x's. Taking these 2 numbers and dividing them, I get -1.333. Or I get a new fraction, 1.5 over 1, -1.33 over 1. I had a net change of 3 y's over 2 x's. I can change that to a change of 1.5 y's per 1x. I had a net change of down 4 y's over 3 x's. Dividing those 2 numbers, I have a net change of down 1.333 y's per x. We now have 2 numbers that can be compared because we are talking at a per x unit basis. We've taken out the space we've provided context. What do you think, where do you think the function underwent the most change now? Tell your neighbors. $1.5 y's per x is larger than 1.33 y's per x. I would say that the function underwent more change from here to here because I just created a rate of change. A rate of change are values that you can compare. You can compare how quickly things are moving in a y's per 1x basis. This is called an average rate of change of a function. It's change with context. It is just the slope connecting 2 points. It is just the change in your y's divided by the change in your x's. Your finishing y minus your starting y. Your finishing x minus your starting x. You take those two values, divide it, you get a number. With that number, you now can say, on average, this is how much my function is changing. On average, this is how f of x, or whatever function is, how quickly it's going up or down per x. Okay? I'm going to pop back up, and I'm going to provide the statement. This 1.5. If you have space, put it down. If you don't, write it. Row table. I'm going to break you up. This number 1.5 can get translated to, on average, my function f of x increased 1.5 y's per x. I can take the 1.5 and put it under over a 1. These are my y's, these are x's. It increased 1.5 y's per x over the interval 0 to 2. The answer I got here was negative 1.333. What would your statement be for this one? For this negative 1.333? I'm going to call on the people who are looking outside. Say it. Say it. Say it. No. No, you're not thinking.
By 1.33 y's per x.
Per x. Y per, it's just slope, but it's a unit rate of change. It's just slope, but here's the problem with slope. A lot of people would have kept negative 4 over 3, and you would have said, oh, this is down 4 y's over 3 x's. I want you to change that perception to negative 4/3 over 1. On average, I went down 4/3 of a y per x over this interval. Or, on average, my function decreased, thank you, you are correct, decreased either 4/3 of a y per 1x or negative 1.33 y's per x over the interval from 2 to 5. We get comparable rates of change, we get context. Higher. So when we say decrease, I wouldn't put the negative actually. When we say decrease, I'd say it decreased that many y's per x, which is why I got that negative value. And that's an important thing with average rate of change, people. If your average rate of change is a negative value, you say your function decreases. It's going down from left to right. If your average rate of change is positive, you're saying your function increases. We will continue to examine that after lunch. Okay. What did we learn? Slopes are average rates of change. Provides a comparison, provides context. We don't like keeping fractions. We'd rather say we have an amount of y's per 1x. It makes numbers more comparable. The statements we have after finding a slope is, on average, this is how many y's my function is changing per x. Okay? So I had a slope that was 3/2. I'd say on average, my function is increasing 3/2 y's per x, or it's easier to say 1.5 y's per x. If I have a slope and the value is negative, I don't say I go down 4/3. I say, on average, my function is going down 4/3 y's per x, or my function is going down 1.33 y's per x. We now are able to compare these two values because we have made the spacing the same per 1x. The spacing the same, the values are comparable, boom, more change here versus here. Got it? Cool. All right. We still want to know more about this function. Now we have 3 points. Thankfully, we have some x's. What would you like to have if you wanted to understand this function more? Like, if you could request more information to understand this complicated function, what would you like to know? Tell your neighbors. More points. More points. Okay. Boom. Some more points are included. I have more points. Do me a favor. Find the average rate of change of this function from 0 to 1. Now, your neighbors, what are you doing? Don't figure it out yourselves. Be quiet. See if you can figure it out, and then figure it out. And then check with your neighbors. And if you still don't know what you're doing, that's okay. That's okay. It's like, what is it? So, Rock doesn't know. That's okay. Here's what I'm going to say. What is the other word for average rate of change that we just learned? Slope. So if you get asked average rate of change, you're asked slope. If you're given an interval, it's an x interval. So from x equals 0 to x equals 1, what is the slope that connects those 2 points? Okay, we can take these 2 points and connect them with a line if we want to, and we can calculate the slope of this line, and that is the average rate at which the function changes. Find that value, and then please provide the statement so that you're starting to get used to the statement. Tell your neighbors, what is the statement that explains that number 4 that you just calculated? No. The statement is not, that's slope. We're going to get used to it, okay? We find the net change of our y's divided by the net change of our x's. 4/1, we get 4, or 4/1. That's fine. That's good, okay? We say, on average, my function f of x is increasing 4 y's per x. per 1x on the interval from 0 to 1. Please find the average rate of change from 1 to 2 and give me the statements. And then we'll stop doing all this like work, and I'm just going to ask you a question and you're going to figure it out. Go. We could take this point at 1, point at 2. You could connect to the line if you want to see like the line, and it's like, oh, average rate of change is really just slope. It provides like change in context. Please write down the number and then give me the statements, because it's like so easy to calculate numbers, but it's important to understand what it means. Write down the number, then give me a statement. One to 2. Focus. Stay with me. You put in the work now, it's going to help you. Now, we don't have to do the slope calculations, guys. You guys understand change, visual change. 6 to 5, I go down 1 over 1. If you just said that it's -1, fine. That's what I want, okay? You don't have to do 5 minus 6 and 2 minus 1. You can just say, I went down 1 with my y's, I went over 1 with my x's, sure. Now that value -1 is -1 over 1. What does it mean? Ready? On average, my function is what? Decreasing. 1y per x. All right, now here comes the question. We're done like showing work. Now you're just going to do the analysis however you want to do. Over what interval do you think the function underwent the most change? Over what interval is the function changing the most? Go. Great question, McCarty. So, we calculate the average rate of change from 0 to 1, we get 4. From 1 to 2, we get -1. From 2 to 3, we get -2 y's per x. From 3 to 4, we get 1 y per x. From 4 to 5, we get -3 y's per x. From 5 to 6, we get +2 y's per x. Many of you are like, oh, 0 to 1. McCarty's like, oh, no, look at this. If I go from 6 to 5, okay, I'm going down 5. You just found a net change of 5, which is greater than a net change of 4. But McCarty, you're just looking at the y. You don't have the context. Everybody, find the average rate of change for McCarty from 1 to 5. Please find the average rate of change from 1 to 5. And then tell Mr. McCarty, is he right? He found the greatest net change. He's like, 6 to 1, that's a net change of 5. That must be the winning interval. Tell McCarty. Find the average rate of change from 1 to 5. Go. Do it. You get it? Just 1? No. -5 over 4. McCarty, would you gonna change your answer?
Yeah.
Why?
Because the slope is less than some of the alternatives.
Yeah, so yes, you're right. 6 to 1 is -5. You have a net change of -5, which is more than a net change of 4, but then you're missing the whole point. You need context with your change, which is why you realize, oh, that change of 5 occurs over 4 x's, you take these values, bro table, and you divide them and you get negative 1.25. And you can now say, yo, on average, my function decreases just 1.25 y's per x. That is not bigger than 4. And we have comparable values because we're finding slopes and a unit rate, okay? A y per 1x. Cool. What would be nice, though, if you really want to understand the function? Use the graphing calculator. Okay, the person finally was able to give you what the graph looks like. Are you still answering this question the same way? That from 0 to 1, with the average rate of change of 4, that's where the function experienced the most change, or are you going to change your answer again? Tell your neighbors, where does the function undergo the most change? Come on, Aberbell. When does the function undergo the most change? Are you still saying 0 to 1? Is there ever a period, an interval, where we're changing more than 0 to 1, than like 4 watts per hour?
Are we talking about like point?
Guys, now that we have the entire graph, get out of the whole number. Get out of the points, okay? You have an infinite amount of points right there. I'm not even going to say 5 to 6. I'm probably going to say 5.5 to 6. And you guys are nailing it. Mr. Thomas, I saw you. You're like, yeah, between 5 and 6. Everybody's like thinking 5 to 6. Yeah, you're right. That's when the function is changing the most. If I looked at the average rate of change from 5.5 to 6, we are talking about a potential net change of going up 1, 2, 3, 4, 5. We're going up 5 over a half. We are talking about an average rate of change of 10. We would say on average, my function is going up 10 y per x. Guys, this is why we say average. This is why we say average rate of change. This is why on the previous statement we are saying on average, because you don't know what the function looks like between points. We don't know exactly how the function is changing, but we do know on average we're going to have to go up this many y's per x. On average, we're going to have to go down this many y's per x. Okay? And that's the idea behind change in function. You want to analyze the change in function, you need context. You don't just look at y's. Sorry. You don't just look at y. You look at y's per x, comparable values. To provide context, you use the average rate of change. Rock, what's another word for average rate of change? Slope. And you look at not only the change in the y, but you make sure you have that context and you provide change in your x's. You make sure you put this as your number divided by 1. Your number could be a fraction and that's okay. You could say 5/4 of a y per x. That gives you your unit rate of change. You're able to compare how quickly things are changing to each other because it's like per x, okay? More intervals, more knowledge. But you're still just talking about an average rate of change. You still don't know exactly what the function is doing, but you have a good idea. Okay? Cool. From 0 to 2, Please find the average rate of change of this new function g of x and give me the statement describing what you've just found. Go. Tell your neighbors, get the answer, give me the statement, go. From 0 to 2, it's right there. It's easy to calculate the values. I want you to write down what the values mean. Everybody's calculated slopes so many times in their life. Write down what it means. Nice. Careful, careful. Your y's, your function values per x, the interval, the spacing. The y's are what we're paying attention to first, how your y's are changing, but the context is the spacing of the x's. Your y's over your x's. Okay? Nailed it. Guys, you don't need to use the slope formula. Okay? Some people make mistakes when they use the slope formula. You go down 1 over the course of a spacing of 2. You don't say I go down 1 y and over 2 x's. You say on average, my function goes down a half of a y per x over the interval from 0 to 2. You think about this being over 1. 1/2 over 1 is the same as 1 over 2. On average, my function decreases a half of a y per x from the interval 0 to 2. Is it decreasing at that rate consistently? No, it's doing different things. It's like it's increasing a little bit, actually. It increases a little bit, then it decreases by more. This is why we say on average. Do one more, 0 to 7. 0 to 7. And it's going to be a fraction, and it's not going to be able to simplify to a decimal that you know. Be okay with that. Give me the statement. Maybe you use the slope formula for this one. Don't change it to a decimal. You don't know what it is. On average, the function decreases this many y per x. Now, some of you like to draw lines. That's fine. Some of you like to use rise over run. That's fine. Some of you like to use the formula. Y2, my ending, my finishing y minus my starting y over my finishing x minus my starting x. That's how we get -3/7. Okay? Now, that's -3/7 over 1. So we can say on average, my function, I guess, what is this, g of x? G of x decreases 3/7 of a y per x. Got it? Again, it's on average. We don't know exactly how it's changing. I mean, we can actually see how it's changing. More subintervals, more analysis. All right. Hit me with 3 to 6. You're given a table. Go. Can you find and explain what you found for a table? We don't have to do all of them. It's just a little bit unnecessary. Do it. No, do 3 to 6.
3 to 6? 3 to 6? Up 3, wait, up 4. 9. Up 4.
Oh, gosh.
Up 9. 3 to 1. Oh, on average, my function. No.
It's very important to understand what are your x's and what are your y's. So you notice these are my x's, these are my function values, y's. We are talking about how the y's are changing. The x's just provide the spacing. It's like we covered this many y's over this amount of space in the x's. The x's provide the context. We want to kind of remove that spacing by dividing the two numbers and get it a per x basis. I end at 12. I started at 3. I had a net change of 9, while my x's had a net change of 3. 3. On average, f of x went up 3 y per x. Do 2 to 3. Go. Go. Get it, everybody. Stop waiting for your friends to get it. Don't be afraid of being wrong. Be afraid of just waiting and not trying. This is what we got to do. We got to struggle more earlier on. No, just let's get the statement right and check your statement.
Yep. Go.
You did under the chart.
Well, I was like,
Make sure you know how you're getting that value. You know how you're getting that value? All right. Okay. Now, if you didn't have context, you'd probably say that going up 9, you'd say up 9 was more change than from 2 to 3 down 6. But you can't compare up 9 and down 6 unless you provide that context. The spacing, eliminating the spacing, providing a unit comparison. -6 y's per x compared to 3 y's per x. Faster. The -6 is bigger. That would be more change on average, okay? On average, f of x decreases 6 y's per x over the interval 2 to 3. More change on average. Less, even though there's more net change. Eliminate the spacing. Cool. This can be applied to real world scenarios. Here we go. We have a situation. There are snow amounts on a balcony after a certain amount of hours, bros. Tell your bro friends, what would you consider X's and what would you consider Y's?
I would just say the inches is the Y because it's in the corner. Yeah. It literally says it right there. So.
Input at this many hours, this many inches of snow. Very important, guys, because if you're finding slope or if you're looking at things, would you want to be told by a weatherman? Now, we put this because when we were making these notes like a week ago, it's like, hey, let's do some snow because it's so hot outside. Would you rather a weatherman tell you, hey, it took 2 hours to increase 1 inch? Or would you rather hear, hey, inches per hour? What makes more sense? What is more used more in the real world? Hours to accumulate 1 inch or inches per hour? Tell your neighbors. Yeah, it just makes sense. Inches per hour is how we do it. Y's per x, inches per hour. So make sure you put your inches per hour. Okay. Find the average rate of change from 2 to 12, and then give me, don't write down the statement, but tell your neighbors what the statement would be. What is the average rate of change from 2 to 12? Not 5. 2 to 12. Not 2. Not 5. You're doing this. You're doing hours per inch. 5. 5. You're doing hours per inch. We want inches per hour.
It's evident in the chart.
Inches per hour.
Yeah.
Inches. Increase 2 inches. 3 minus 1 inches. Finish minus start. Over 10 hours. Inches per hour, guys. We just talked about that. You guys all told me, and then you said 5. You put the X's over the Y. You said hours per inch. This is 1/5. Now, here's the easiest way to provide a contextual statement that is always correct. Look at A. Make sure you understand what A is. Inches of snow outside the door. I'm going to use that in my statement. I will say, on average, the amount of inches of snow outside my door is, now we use a number, is increasing by 1/5 of an inch per hour, per 1 hour. Not 1 inch every 5 hours, it's 1/5 of an inch per 1 hour. Put that over a big fat 1. Okay. Do it for this one now that you guys know what you're doing. Go. Or at least tell your neighbors what the statement is. Go. 20 to 24. Right. The value is -1. We go down 4 inches over 4 hours. On average, the amount of snow on our balcony in inches is decreasing 1 inch per hour. What could be happening over the course of the day? Snow falls, and then it starts to melt. Change is right. Change is what's happening. That's what life is. Change. Cool. Here's the height of the tree. When's the tree growing the fastest? Guess what? You're not going to be able to answer this question with 100% certainty. Which is why you are answering the question, when do you believe the tree is growing fastest? We only have a limited amount of information. Remember that graph? Points are cool, but you don't really know exactly. This is why we say on average. But when do you believe the tree grows the fastest? Go, figure it out. What would you do to be able to answer this, Nancy? How can you have an educated guess of when you think it's the fastest? I don't have the graph. I just have this table of information. Okay, what do I do with the table? Do I say, 2 to 6, that's 4. That's a big number. 6 to 11, that's 5. That's a big number. 11 to 15, that's 4. This is a half. Do I blindly say this is going to be the biggest change? No. You need the context. You find the slope.
There's no graph.
No. 5 to 7.
So, I don't like this. I'd probably rather this, I'd probably change the years. This is misleading to the purpose of this lesson. If you just looked at the Y's, you'd probably say 5 to 7 is 5. You can't say that definitely is the fastest growth unless you provide the context of the spacing of the time. You need to say, oh, 2.5 meters per year. 4/3 meters per year. 4/2 meters per year. 1/2 of a meter per year. You need to look at as many slopes as you can, but the slopes. You need to look at as many rates of change as you can. You need to not just look at the y, Mansky. You need to look at the y's over the x's. You need the context. You need a comparison. There's your comparison. After that comparison, I am saying probably from 5 to 7. Cool. Keep going. Oh, here's a challenge one for all you smarties out there. I don't have the points on my function, but I know on average how my function is changing. I don't know the points on my function, but I do know on average how my function is changing. Could you use this information to know where your points are? Let's see. Try. Don't just sit there and wait. Too many of you guys just think that lesson time is checkout time. Try. Nope, turn it back on. An average rate of change is given to us. I know how H is changing by looking at this table. I know how H is changing. Use this information to tell me what that point has to be at 1. Try. Let me see. I like what you're doing, Gula, but it's a little bit easier than that. I like what you're doing, Walsh, but you made a mistake. Good, Swanee. Try. We got this. Try. I want you guys to make mistakes now. Ooh, going too far. Are you backing up? That's crazy. Start here. Yo, good start. But you made a mistake that everybody makes. Okay, ready? I know I start at 4. I know what this means. This means on average, H decreases 5 y's per 1x. Well, if I started with a y value of 4 and I decrease 5 y's per x, obviously I'm going to have to subtract 5 and get to -1. Many of you got that. Cool, good start. But then you guys blindly keep going and you make major mistakes. Ready? If you put 3 here, you are wrong. Fix it. It's not 3. If you put 3 there, you are wrong. Fix it and figure out why. Yo, focus.
I think I did it wrong.
Turn your brain on.
Oh, you did it different. No, wait, I'm done.
Fix it.
I know. Next one. That's 4 per inch.
Nice.
I don't understand.
You got to know what you're seeing. Bro table is all on it, and they're very loud so everybody can hear it. Okay, ready? Because we're focusing and we're paying attention and our brains are not off, or else Mr. Messer knows when your brain's off and he just hounds you. My function is going up 4 y's per 1x. But over an interval from 1 to 3. That's 2 x's. I go up 4 y's per x over the course of 2 x's. How much do I go up over 2 x's? 8. You go up 8. You got to get to 7. Keep going. You get it? Listen to Ho, he'll tell you. Why? No, you're not paying attention to the lesson. You're just trying to get answers. Ready? What does this mean? What does this mean? My function on average goes down 5 y's per x. I started with a y coordinate of 4. I go down 5 y over 1x. Go down 5. Got it? All right, let's explain the next one again. Again, you guys are such like, you got to raise your level of lesson understanding. You guys are all about answers, but you're not understanding where they're coming from and why you're getting the answers. You guys are slope calculating experts. But do you really understand what you're doing? Pay attention. What does this number 4 mean? On average, my function is increasing 4 y's per 1x. So I'm going up 4. Every x I move over 1. From 1 to 3, that's 2 x's. So from 1 to 3, I got to go up 4 twice because I'm covering 2 x's. That's how I know I go up 8. Because I understand what an average rate of change means. Keep going. You would think that's I'm going up 2 per x, but I've covered 3 x's. I am going up 6, getting me to 13. Going up 6 over the, I'm going up 2 per x, per 1x. There's 3 x's. Because what's 7 plus 6? Because I'm starting at the point 3, 7. My function goes up 2 y's per x on average from 3 to 6. 6 plus 7. All right. I'm starting at 13. I go up 7 y's per x. I get to 20. Okay, geniuses who now understand, because maybe now you're paying attention. Maybe you now know what an average rate of change is. Do this one. You copy or did you figure it out? And then you copy? All right, good. Yeah, I think you got it. No, really good on the last one, too.
Are you sure this name is on it? Wait. Is it name on it? How? What?
Robert, you get it? You got to get, on average, up 6 y's per x. I got to be going up to get to that value. And then I got to go down to get to that value. All right, we got to move on. Bring it back in. Because I now know what average rate of change means. My function's going up 6 y's per x. My interval is 3 x's. My function's got to go up 18. From -2 to 1, I got to add 18 to get to this point. My function goes down 3 y's per x over the course of 1x. Okay, so I got to go down 3 to get to 4. From 2 to 4, I'm going up 3 y's per x. Okay, I got to go up 6 to get to my next point. From 4 to 7, I'm increasing 2 y's per x. I got to go up 6 again. Well, going to the right is easy because the addition makes sense. 4 plus 6 is 10. 10 plus 6 is 16. Well, instead of adding, if you're going the opposite way, subtract. 4 minus negative 3. Or what number minus 3 is 4? 7. 7 minus 18. Or what number plus 18 is 7? That's what we got to figure out. Okay? If you know average rate of change, this makes sense. If you're just like a slope calculating person who doesn't understand what's going on, yeah, I don't know how to do this. Next. Yes. Schweiry.
I found that but I found -1 and -3.
I have to go down 3. My average rate of change from 1 to 2 is -3. Which means on average, my function's got to go down. The y's have to decrease. I got to go from 7 down 3 to get to 4. My y's have to go down. Okay? Okay. Log it up. A student earlier was like, this looks hard. This is not hard. You now have an equation. You're asked to find how this function is changing on average over an interval. Rock, what is another word for average rate of change? I'm not picking on you. This is fun. We're like, you'll be my slope guy, okay? You are asked to find the slope. This is your x's. Okay, you have the bottom of your slope. How do you get the top of your slope? Plug in the x's to find your y. Calculate the slope. That's it. And when you calculate the slope, you are finding a rate at which this function is changing on average. Plug in 1, I get 4. Plug in 3, I get 18. Finish minus start. On average, my function x squared plus 3x increases 7 y's per x over this interval. Do this one. Go. Y per x. Yes, you did. You wouldn't do hours per inch. You wouldn't do x's over y. Come on. Why do I come over here?
I did get it right the first time.
All right, we'll get to the next one.
I got it right the first time. I got it.
Get the next one.
I'm doing it right now.
No, I'm not praising anybody at this table. I'm making sure you guys are all like up to date with what we're doing and paying attention. Thank you.
I don't get it.
You just calculate the slope. These are your x's. You plug in the x's, you get the y. If I plug in 1, I get 4. This is the point 1, 4 on the graph of x squared plus 3x. I plug in 3. 9 plus 9 is 18. That's the point 3, 18. Do you know how to calculate the slope between 2 points? That's it. That's all we're doing. Don't say you don't get it. You're going to, like, don't get it yet. Okay, we got to keep going. This is your interval. These are your x's. So that's the denominator of your slope. You plug in 1. A negative power is like dividing an amount of times versus multiplying. This is 8 divided by 1 once. That's 8. Somebody's blowing up. 8 divided by 4 would be 8 times 4 to the negative first. That's 2. This is where we finished. This is where we started. Don't make a mistake. 2 minus 8, my y's went down 6. 4 minus 1, my x's went to the right 3. Divide that, get a unit per x. On average, my function went down 2 y's per x from 1 to 4. Got it? Okay. The last thing we need to talk about. I'm going to fill this in for you. Find the average rate of change of 3x plus 4. Well, I'm going to add 3 as I add 1. So I got 3 over 1. Okay, that's just 3. I'm going to do a little bit of calculations over here. I say 3. I will continue to find the average rate of change. And I get 3. If I did the same for this function, let's see. I got 3, negative 3, negative 9, 7, 11. I see I go down 4. Oh, I messed up. 2 is negative 1 and negative 5. I see I go down 4 as I go up 2. I go down 4 as I go up 2. My slopes are all negative 2. What do we notice? That for lines, the rates of change is the slope of the line. Lines have constant rates of change. And the rates of change equal the slope of the line, the m of the mx plus b. We'll use that to our advantage in the future. If we looked at quadratics, what we would notice is that the rates of change will be linear in their change. And I will finish that up, and if you don't pay attention, you'll figure it out on homework. There's one homework problem, the motion question. Don't freak out about it. It won't be on your quiz or your test. Oh. The average rate of change is 6. Then negative 2. I'm going to have to pull this back up. Six, negative 2, 2, 6. Negative 6, negative 2, 2, 6. Negative 6, negative 2, 2, 6. What you will find is that there's a pattern in the average rate of change. The average rate of change will always have a linear pattern. The change in the change will be constant.
There's only one.
Cool. The average rate of quadratic has a pattern. Or the change in the change is constant. You will see the pattern for all the average rates of change. Here, I plug in negative 2, get 4 times negative 2, negative 8 plus 3, negative 5. 1, 3, 1, -5. What happens? Add 6, add 2, subtract 2, subtract 6. All of these are over 1, plus 1, plus 1, plus 1. So those are my rates of change. 6, 2, -2, 6. Subtract 4, subtract 4, subtract 4. You can do the same thing here. You'd see that the rates of change consistently.